in the bicycle problem, there are two cyclists. One of them is traveling at a constant speed of 10 meters per second. They pass a cyclist who is traveling at 5 meters per second. And in that instant, the cyclist who is going slower begins to accelerate at a constant acceleration of, is it 1 or 2 meters per second squared? 1 meter per second squared. Now this suggests eventually that the second cyclist will speed up, at least matching the speed of the first, probably increasing past that, and then eventually overtaking the first cyclist. Does that make sense? In fact, you had this problem at the very beginning of the year, albeit a little different, but not much. If we assume that the origin is when the two bikes are at the same place, then bike 1 is traveling at a constant speed. Therefore, on a position versus time graph, their graph would look like that. The second cyclist, though, is traveling at half the speed initially, but then begins to accelerate. I think they're going to look something like this. That suggests there's a point in their future where they'll meet. So let's consider cyclist 1. There, that's a cyclist traveling at 10 meters per second. They're going to travel some distance. Now, they're not accelerating. So if you look behind me, cyclists not accelerating. That means putting in 0 for all those A's, right? Look at what that does. If you're able to follow along with me, if I put 0 in for A here, that means the final velocity and the initial velocity are equal. Well, duh. The velocity's not changing. That also basically takes away the term right here in delta x, wouldn't you agree? Leaving you with just one relationship that relates position with velocity. Distance equals rate times time, the old middle school formula, one that you have been taught. But I'm just showing you where you could get it from if you had the acceleration to 0. Now the other cyclist, traveling at half the speed at time 0, begins to accelerate at 1 meter per second squared. If I were to look at what I know about the second cyclist, I know their initial velocity is 5 meters per second. I know their acceleration is 1 meter per second squared. I'm going to go ahead and make this way the positive direction because that just makes reasonable sense, right? I don't know anything more, which means I only have 2 pieces of information. And therefore, it's going to be challenging for me to solve for a third. Now, this is where this problem transitions from being what I would argue is super straightforward and easy, like what you had for your quiz. Plug and chug. As long as you can figure out 3 things, you can plug it into the equation. Yeah, there's a lot of places you can make mistakes, like not putting the minus signs and the plus signs in the right place. But what you had for your quiz today, I would call a level 1 problem. This one, maybe a level 2 problem. It's harder. You have to understand something more about what's going on, but not too much more. Cyclist number 1 has a relationship between displacement and time that looks like that. Their displacement equals 10 times the time because they're going 10 meters for every second. They have displacement and time as variables in their function. Can I create a relationship with this information that would relate position with time? And I'm sure that I can, because I could just ignore final velocity, and that should create a relationship that has position related to time. Correct? All I need to do now is find out when these two folks are at the same position at the same time. I'm thinking substitution. I have two equations and two unknowns, something you have done in Algebra 1. You should be able to successfully eliminate one of the unknowns and solve for a known. I think the easiest way to do this problem is to eliminate displacement. That will leave you with a single variable in your problem that you can solve for. Of course, you guys have those fancy calculators, right? You could plot this. Y equals 10x. Y equals 1/2 x squared plus 5x. And plot it right on your calculator and find where the two things meet. You guys bought those things. Why don't you use them, right? You know stuff. You're smarty people. I would never use my calculator for that because I don't know how. I don't have one. Every time I bought one, I had to give it to some stupid kid. You guys, well, not stupid. I'm recording this. These kids are wonderful. They're never stupid. We believe in them with all of our hearts, mommies and daddies who eavesdrop on this conversation. So I'm going to go with the old school way, the one way I like, and realize that should get me to a solution. Now, this will figure out time. You're likely to get 2 times, by the way, and this is actually a pretty easy one to do. I don't want to do the arithmetic for you because I think that's beneath you to have me do arithmetic. You're paying the big bucks to see me. I can do lots of things. Arithmetic seems like the lame thing to do. But I also know that there's a person in this room, and it's more than one based on your math pretest, who probably needs to see the arithmetic done a little bit. That brings me great distress. But I have no choice but to say that when you subtract 10 from both sides, you'll get something like this. And you shouldn't divide by t, because that's incorrect mathematics. Because you'd be dividing by potentially 0. You're supposed to factor out a t. Like so. And that means t equals 0 and t equals 5 divided by 0.5, which I'm pretty sure is 10 seconds. Which of these two answers is correct? Both of them. Understand something about what math is telling you. And I'm not trying to make a fool of you. I'm trying to make you understand something about this. You think this is a math class now because we're doing all this math. What I'm telling you is math was not invented to just have you guys sit in a classroom and run numbers together. At one point or another, somebody wanted to know if they had more apples than somebody else and they counted them, right? This is just a long extension of that. Math was created for a purpose. This is part of its purpose. The reason there's 2 answers is we asked the math to tell us when the 2 objects were at the same place. It gave us 2 different times. They were at the same place at time 0, and they were at the same place at time 10 seconds. Now, one of these times is what you want to use, but both times are correct here. I'm going to use the 10 seconds because I want to find out the other position when they are at the same place. And I can choose to put it in this function or that function. So I'm putting it in this function because it's easier to tell you it's 100 meters. All right, problem. You'll be creating 2 equations that look like this. It's just that one of them is going to say 1,000 minus d. Does that make sense? All right. Only one thing was accelerating, so only one of the equations had a t squared in it. In this one, you're going to set up 2 sets of motion equations. The difference is, in this problem, they're not traveling in the same direction. So you have one train here going this way, and one train here going that way. And you're told how far apart they are at time 0. So you have a separation distance. What's the separation distance? What's the separation distance? How far apart are they when they start? 1,000 meters? They're going to meet somewhere in the middle. I don't know where. I don't know any of the parameters of the problem. I don't need to know these parameters. So here's the thing. Unlike the other problem where they both moved the same distance, in this problem they did not. This train is going to move a distance d. This train is going to move a distance 1,000 minus d. This is the displacement for one of the trains. This is the displacement for the other train. They both will have D in them, and they're going to meet at that point at the same moment in time. So T will still be a common variable. And you have the initial velocities for both trains, I believe. So you'll be able to run this problem in a very similar manner. I'm going to encourage you to consider direction in this problem. You don't have to unify the direction in the problem. You can have positive be this way for this train and positive be this way for this train. But there is some value in making positive the same direction for both things, but it's really arguing not a particularly interesting point. So try this one out. I'm giving you a lot to go by. After this moment, it's exactly the same as this. All right. Nobody asked about the speed of sound question. And it's like number 4. So I know it's early in the homework, and that means you didn't make it very far. So that's a good one to have asked about, and it's too bad. I'm going to encourage you in the future when I give you homework, please start it earlier, because I am done with the content. All of those problems are yours to be able to do. I will add new content that has nothing to do with that homework now. You're practicing in the rears of us covering the material. Does that make sense? That's why I posted it several days ago. So please work ahead. Start immediately. Do 15 minutes a night. It will work better for you. Or you're going to be asking me when you can retake this test. And I don't want to have that conversation on the first test. In the speed of sound question, I think you should pay attention to the way the problem is phrased, because there's several questions out here that are kind of stylistically different, and this is one of them. In the first part of the problem, you're told that a pebble is dropped, and you hear the splash of the pebble hitting the water 7 seconds later. And you're asked to figure out how high the bridge is from the water level. So that part of the problem isn't terrible. I ended up making downwards positive, and we're looking for delta x. We know the initial velocity is 0. We don't know the final velocity, but the acceleration is that due to gravity, 10 meters per second squared. I'm making that positive, and we're told that it takes 7 seconds for the pebble to reach the ground. This is a very straightforward question and shouldn't take too long for you to do because it's a plug and chug. You pick a relationship that has everything except for final velocity in it. You plug in the values and you get 245 meters. The more interesting question relates to the reality of this problem. Because in the reality of this problem, you hear the splash after it happened. Because it takes time for the sound waves to propagate from where they originated from to where you're standing on the bridge. Now, to do the problem properly, you'll need to take that into account. And they tell you in the problem that sound travels at 340 meters per second, a constant, which means that the sound, and I'm skipping a little here because we've already done this, will have a relationship between how high the bridge is and how long it will take the sound to get there. Everybody follow that so far? So the truth of the matter is, it takes less than 7 seconds for the pebble to reach the water, because some time is required for that sound to get back to you, for you to hear it. So I would subtract that amount of time from the 7 seconds. If you do this, you'll be able to create a relationship we don't know what the height of the bridge is, but we know that it takes slightly less than 7 seconds for you to hear the sound, and it takes that amount, that slightly less part, for that sound to come back to you. So the first version of this problem, kind of stupid simple. The second version of this problem, I'd go maybe level 3 hard. That's a tough one to put together. I know it's number 4. I don't care. I like this question. I think it's good. I think it's thoughtful. But also consider this. If you did this problem already and found the original height based on the first part of the problem, 245 meters. That's what you get for part A, 245 meters. And you know that sound travels at 340 meters per second. You could have estimated how long it takes sound to move to know whether your problem is right or not. The bridge is slightly less than 245 meters, but it'd give you the ballpark of what to expect your answer in. Does that make sense? So, folks,